Good morning, everyone. Thank you for joining us this morning for our second installment of our Moldflow webinar series this morning. This morning we will be going over how cooling line and mold design are affecting your plastic part cost and performance. My name is Scott Bradley. I'm with D3 Technologies. I am an account executive within our Advanced Manufacturing Solutions. Joining us as a presenter today will also be Eric Foltz, the Senior Managing Engineer with the Madison Group. And just a little background on D3, who we are. D3, we are a national Autodesk partner with over 15 locations to serve our customers throughout the United States. We have been a top manufacturing partner with Autodesk for over 30 years. Recently, as of a few years ago, we have reached the platinum partner level status with Autodesk, and we focus on all manufacturing and plant industries within the Autodesk solutions. So in addition to all of the core technology solutions that we specialize in here at Autodesk and D3, we also are certified in the simulation tools, CAM, PDM, our engineering to order or ETO, and our product lifecycle management, PLM, Autodesk Forge, and the Autodesk Cloud Solutions. Today we're going to be focusing on Moldflow, which is part of the Make specialization, which we have also received our certifications in as well with Autodesk. Here at D3, we are a part of that platinum status is our ability to serve our customers through advanced technical support, as well as training and mentoring support for all of the solutions. And here at D3, we utilize a virtual online platform called CAD Live, powered by D3. So CAD Live allows us the ability to train all of our customers live instructor led with a virtual platform. So it is a classroom environment, all virtually led throughout the United States. So it allows us to have face-to-face interaction. We're going to be able to see your screen, see our screen, clicks and picks, all while maintaining a very interactive classroom environment. Along with that, our CAD support team and our technical support team here at D3 are among the best ranked in the Autodesk reseller network. We receive a very high rating, a large team there that are staffed every day, ready to take any type of email, chat, or phone calls that do come in for our customers that are needing assistance. We don't let that go to any recordings, and we're gonna get right to that with a very quick response time. So when I say the Make certifications within Autodesk, these are the products that I'm referencing. So we work with the Make solution anywhere from the generative design tools all the way down to CAM. And this is an area that Autodesk and D3 have put a lot of resources over the past few years to really develop the capabilities in the products within our portfolio. Of course, today we're going to be focusing still with this being the Moldflow webinar series, going to be focusing on Moldflow, which is a big part of our tool and die and injection mold customers. But we also have capabilities in the CFD, the computational fluid dynamics area, simulating fluids, fluid flow, recirculation. We have an additive division department, so we're going to be working with tools such as Autodesk NetFab. And then so some future vision tools such as generative design, helping engineers really amplify their design output utilizing AI and a lot of automation. So within the Make channel, Autodesk and our partnership with the Madison Group, where we're really taking on a lot of these solutions and really building out our capabilities within the Make portfolio. And with that, we'll jump right into the webinar series this morning, and it's going to be covering how cooling line and mold design are affecting your plastic part cost and performance. And Eric Foltz will be taking over at this point from the Madison Group. Eric, are you ready to take control of the slides?
Yeah, I think so. Thanks very much for that introduction, Scott.
You're
As
welcome.
Scott mentioned, yeah, as Scott mentioned, my name is Eric Foltz, and I work for the Madison Group, and we're that partner with D3 that's helping customers fully optimize everything from their plastic part design all the way through the manufacturing, the tool and design process, optimizing their process so that we not only get cost-effective parts that look good, but they're also going to perform in the field. So part one focused on what can we do for optimization before we have the mold design, and this part two we're going to start talking about how our cooling line and our mold design overall is going to affect our plastic part cost and performance. So why are we focusing on mold cooling when we're talking about the injection molding process? Why don't we talk about filling faster? Why don't we talk about packing? Or why don't we talk about part ejection? You know, all of those are important steps of the injection molding process, but when we look at the injection molding cycle overall, when we see what dominates the injection molding cycle, it is the cooling time. So in today's environment where we are, we're worried about, reducing costs but keeping quality up, the cooling cycle or the cooling portion of the injection molding cycle, when the part is just sitting in the mold and we're not making any parts before we eject it out, that's what we're trying to cut down so we can bring our costs down on our part. It is the easiest way for us to improve efficiency, and it's the easiest way for us to help control the quality of the part overall. Also, cooling influences each stage of the injection molding process. So even though we divide the injection molding cycle into maybe a fill, a pack, and then a cool stage, cooling overall and how we're going to cool our plastic part does influence each stage. When we talk about when we're initially injecting that material in, we call that the injection phase. Cooling is going to influence the injection pressure we're going to require to fill that mold. Colder molds are going to require higher injection pressures. It's also going to influence how our part sets up and how we develop a frozen layer up against that cold mold wall. And that will, in result, influence our residual stress in our part. And ultimately, it will also influence how our part is going to look. Here on the right-hand image, we are seeing two tensile bars that were molded at two different mold temperatures. And we can see with the colder mold wall, we are going to have a thicker frozen layer fraction, material that's going to freeze upon contact, than if we run a hotter mold overall on our part or on our mold. Again, cooling is going to also influence us in terms of our packing time. Packing, we're trying to compensate for that material shrinkage as it's cooling from the molten state into the solid state. So, cooling and how we're going to cool this part is going to influence the packing time and therefore our packing weight or our part weight. And it's also going to affect the aesthetics of our part. How likely are we to develop sink marks or voids in our part as well? So it does influence the packing stage as well. And of course, cooling is going to influence the cooling stage. Mainly there, our cycle time, which comes down to our part cost, and also our surface appearance. We can see with these two images, with a cold mold and the same material, we can get a very dull matte finish on our parts where weld lines become very prominent. We see a lot of read-through in our parts, and maybe the part doesn't look as good. But with the same process and just running the mold hotter, you can see that we can get a much more aesthetically pleasing part that hides those knit lines and overall has a much better consumer appeal for our part. And again, like we said, how we cool this part is going to influence our residual stress in our part, and because it influences the stress in our part, it's going to influence the dimensional stability of our part, how that part's going to deform after it gets ejected out of the mold. But while cooling has an influence in each of those stages, how do we actually evaluate these molds that we're constructing? And generally, the way that we're going to evaluate it from a purchasing side is, well, how much does that mold cost? What's the upfront investment that we have to make in order to build that mold? And then from a production standpoint, what's our cycle time? How quickly can we manufacture these high quality parts? And what part cost is that going to be implemented to our customers or be imparted on us, the manufacturers? And of course, no process is 100% efficient, so then we're also going to evaluate our mold based off our scrap rate. And usually there are big red flags are part aesthetics and dimensional stability. And again, we already highlighted how cooling is influencing those different aspects. Cycle time, hotter mold, longer cycles, scrap rate, dimensional stability, and aesthetics, also influenced by the mold cooling. You know, and so when we're trying to look at evaluating how to get the most out of our tool, the initial, knee-jerk reaction is, well, in order to improve efficiency and improve yield and have shorter cycle times on our part, let's run this mold colder. We're putting a hot material in there. If we run the mold cooler, we're going to have a greater delta T, a greater temperature difference between the hot and the cold, so we should be able to cool that part faster. However, we've just done some studies here where we look at cycle time change versus the mold temperature or influencing the part thickness of our part. And what we can see here is that while yes, as with the blue line, as we run a colder mold temperature, we can get reductions in cycle time. Really, if we're looking to optimize our cycle time, we should start looking at our part design and our wall thickness on our part more than just running the mold cooler. So we're not going to see as big of a bang of a buck just by running the mold colder. If we're really trying to optimize cycle time, we should go ahead and address all those issues that we talked about in our first webinar series with optimizing our product design and trying to keep as thin a wall as possible. The slope of this line, the red line with the part thickness, is much steeper, meaning it's going to have a much greater influence on our cycle time than just running the mold cooler. And then when we go beyond the manufacturing process, the other thing that cooling is going to influence is our part performance. Not optimizing the mold temperature is not only going to influence our costs, but it is going to influence our part performance. It's going to influence that dimensional stability. It's going to influence the crystallinity of our material if we have a semi-crystalline material. It's going to influence the molded in stress of our part and, again, our appearance. So from an OEM standpoint, I should care about the cooling because it is going to influence my part aesthetics and my part performance. To show that as an example, here was a study that was done by one of the resin manufacturers, Bayer, now Covestra, where they molded different nylon parts. These are unfilled nylon parts. And they measured how the part shrunk and when the shrinkage occurred. So overall, when we look at these bars, we're looking at the shrinkage of the part in the longitudinal direction or the length of the part versus the transverse or across the width of the part with a cold mold wall here and with a hot mold wall. And so if we look at the overall height of these bars, we see that the higher mold temperature here does yield greater shrinkage on our part. So that means we're going to have to build more shrinkage into our tool. But really what's more interesting here is that when does the shrinkage occur? When we look at running the mold cold, we see that we get about half the shrinkage happening almost immediately after the part is ejected out of the mold. And then there's another 50% change in dimensions after the part has been cooled and is fully set up about a week later. If we run the mold hotter and have a slightly longer cycle time, we see that we can really control the amount of warpage that our part's seeing and have a much more dimensionally stable part outside of the mold. The red portion of our bar is much greater than the green portion of our bar. So while the hotter mold is going to result in a longer cycle time and more shrinkage, we can control when that shrinkage happens better by running this mold hotter. Also, by running the mold hotter, it's really important that if we have a material selected that's a semi-crystalline material, we want to make sure that we're taking care of that material. We're allowing that crystallinity of the material to develop, and that degree of crystallinity in our molded part is heavily dictated by the mold temperature and the cooling rate we impart on the plastic during manufacturing. You know, maybe you say, well, Eric, you know, it's tough to measure crystallinity on my part. You know, it's not something I can do in line, and it's not something I can necessarily measure and quantify easily across a lot. But really the reason we're talking about crystallinity is here it's going to really influence our long-term performance or our creep performance of our plastic part, and again, our high temperature performance of our part. Maybe not so much of a difference at room temperature, but our high temperature performance. So if we're looking to use this in elevated above room temperature applications, then that's going to influence us. Also, it's going to influence our chemical resistance. If we don't develop that crystalline structure, we're going to yield ourselves more susceptible to ESC or chemical attack because we're not developing that structure. So by running the mold hotter, we get more crystallinity in our part, and we're going to see better performance in terms of the creep, high temperature, and chemical resistance. Here's an actual example where a high temperature aromatic nylon material was molded at different mold temperatures. So here the red line, this was molded at a mold temperature of 159 degrees centigrade. And then the purple line is with a mold temperature of 57 degrees centigrade. And we're looking at how the stiffness of the part changes with temperature. And here what we can see is at room temperature, so somewhere over here, you can see, yes, there is some difference in our stiffness for our part by running a colder mold wall than a hotter mold wall. But it's not necessarily all that significant. Really where we see the benefits of running that hotter mold and paying attention to how we're cooling that part and making sure we develop that crystallinity in our part is by looking at the higher temperature performance, and not only that we maintain a higher modulus in our material at higher temperatures, elevated temperatures, to give us that better performance there, but also how we drop off in our performance as we get up to that temperature. Here we see a much more gradual, stable change in our stiffness as we increase our mold temperatures. When we don't allow that crystalline structure to develop, we see a much sharper drop in modulus and then much more variability at this higher temperature. So we're going to be less sure how our parts can perform at these higher temperatures. And then again, like we talked about, you know, running a cold mold wall is going to influence our residual stress and our chemical resistance on our part. So here we're showing two polycarbonate bars that were molded at two different mold temperatures, and when we expose it to chemicals we know that attack it, we can see that with a hotter mold temperature we have less stress in our material and we have less pervasive cracking in our part. When we go to that cold mold temperature, we can see that we get much more pervasive cracking and much more likely of a catastrophic failure. And again, that's a kind of a short-term, immediate, measurable cracking. The other thing is that the reason we got that cracking was because of the residual stress, and in our part, our plastic is going to want to relieve any residual stresses in our part. So if we don't cool this part properly, we could get crazing over time, or again, impaired creep behavior or that long-term behavior for our part. And then on the short term, again, with some materials, if we don't pay attention to the residual stresses, we can see a diminishment in the impact performance of our part. Here we're looking at an ABS material where we vary the mold temperature and the melt temperature and measure the impact strength of the material overall. ABS, we usually like this material for its impact resistance. However, we can see that as we go to colder mold temperatures, the performance and the impact strength of our materials significantly drops off just by running that mold colder. As we change the mold temperature, we don't see as much variation. So really optimizing our impact performance of our part, reducing that residual stresses, we got to pay attention to our mold temperature. So how important is mold cooling? I think that we've spent a good amount of time here where we're saying it's very important. We want to make sure that we're paying attention to our mold cooling. So how should we optimize our injection mold cooling? Injection molding, we can think of it, as a contraption that's making parts, but we can also think of it as a complex heat exchanger. And the efficiency and design of our heat exchanger is going to be dictated by our heat input. That's talking about our part design, optimizing that, the material we're selecting, and the melt temperature we choose to run that material at. the heat extraction, that's what we're kind of talking about today, the cooling line layout, the steel selection on our part, and the operating parameters for our mold. How quickly are we moving that coolant fluid into our mold? What coolant fluid are we using? And what temperature are we putting that coolant in at on our part? So you can see, again, just like before on plastic part design, many interrelated components that we have to consider holistically in order to optimize our mold cooling, which makes it ideal for simulation and packages like Moldflow. Again, focusing on part design, we want thinner wall sections to manage that heat, put less heat into our part so we can get quicker cycle times. From a material selection standpoint, we know that for semi-crystalline materials, we require more energy to get that part from a molten state to a solid state. Here we'd be in a molten state. We can see that we have to really take a lot of energy out of this material in order to get it into a solid state, whereas with amorphous material, maybe less energy and less variation over time. So we got to pay attention to the materials. Amorphous materials will probably be able to cycle faster than semi-crystalline materials. And then we also have to, pay attention to the heat extraction. That's the meat of the talk today. How are we going to place our cooling lines, and how are we going to construct this mold so we get the maximum heat extraction from our part. So the way that we generally cool molds in injection molding is we're going to drill a lot of lines into these solid steel blocks of our injection mold. The cooling line placement is usually left up to your tool maker. However, your molder and you have some influence on that as well. And they're going to place those cooling lines based off previous experience and of the end goal of achieving a quote-unquote uniform mold surface temperature. If our part wall thickness is uniform, we fill the part fast so we get a uniform melt temperature in the mold. Once we start cooling this part and we have a uniform mold surface temperature, that's going to yield our highest quality part. In order to achieve that uniform mold temperature, we're going to increase the cooling line density in high heat load areas. So, for example, here you can see we have a lot of cooling lines on our part on the core side of this part where we have a lot of heat load and standing cores, and on the cavity side where we have less heat load, you can see we're going to have less density, these red lines over here for our part. So we're going to reduce that cooling load in those cool areas. And it's often difficult to cooling lines in all the areas that you want. Cooling is usually one of those last areas that we address, and we have to design it around ejection systems or mold actions. So while it may look like, hey, we can get more cooling or, we have a lot of baffles in here, we do have to design around our ejection systems, how we're going to get this part out of the mold as well. And so here, again, we have a lot of baffles, but they don't necessarily go in to this deep core in here because that's where our ejection system is located. So when we look at the influence of cooling line placement, we just thought we'd highlight some of this basic concepts by doing a series of simulations that provide a predicted mold surface temperature of a P20 mold for an 1/8 inch thick plate. And we varied the pitch of the cooling lines, the distance between the cooling lines, and the distance from the cavity as well. We held the cycle time and channel diameter constant. And so when we look and we mold these plates under similar conditions and we have a similar spacing or pitch of our cooling lines, but we vary the depth of our cooling lines, we can see as we get closer to the mold surface, we get a cooler, more uniform mold surface temperature. As we move those cooling lines away, 2.5 times the diameter of the cooling channel, we get hotter mold surface and more mold surface temperature variation. And as we continue moving it away, even more variation. So we'd like to be as close as possible to the mold surface without interrupting the integrity of the mold to get this cold mold surface and a nice uniform mold surface temperature. We did the same exercise where we kept the depth of the cooling lines the same, but we changed the spacing of them. And you can see the closer we can place those cooling lines together, the more uniform mold surface temperature we're going to get. And again, the more uniform the mold surface temperature, the more uniform the cooling, the less chance for dimensional stability issues. But as we said, we can't always get all the cooling that we want. So we have another lever that we can optimize within the injection molding design process, and that's incorporating high conductivity materials into our mold design to improve the cooling line layout. So when we think about most of the tools, materials that we're using when we're constructing molds, we're talking about our tool steels, our P20s, our H13s, our A2s, and we can see that the thermal conductivity of these materials, there is some variation, but in general, they're very similar thermal conductivities. We do have options as a designer, as a OEM, to change those mold materials into high conductivity beryllium copper or beryllium alloys, or copper alloys, sorry, that will increase our thermal conductivity. So if we can't get all the ideal cooling that we want in our part, we can integrate this insert for our part that will improve the cooling on our part without having to have a lot of cooling in our part. We do sacrifice hardness, and these are expensive materials, so the cost for our material does go up on our mold by integrating these. But as we can see here, as we go with higher conductivity materials, here we're comparing P20 and aluminum, you can see that we can get a much different cooling profile in our mold profile with just changing the mold material without changing the cooling line design. And even with something like an aluminum tool that's commonly used for prototype tools, we can see that we don't even need to have nearly as good a cooling in an aluminum prototype mold as we would with, say, a production P20 tool. So to give this a more relevant and real-life example, here we helped a customer. They were injection molding a threaded plug. It was manufactured on a semi-crystalline acetal copolymer. The part designers, they took care and they tried to maintain a nice uniform wall thickness on their part. So they integrated some core outs that were located here to core out and keep a more uniform wall section on our part. So again, they followed that first rule. They're trying to manage that heat input, minimize any wall thickness variation on our part by introducing these cores. So we use Autodesk Moldflow to model in the cooling line layout for our parts. You can see we had just had some drilled lines in our mold in these slides, and we had some drilled lines across the core and across the cavity for these parts. The cores, though, you can notice there's no cooling lines going up into these thin cores. This plug is roughly the size, it's about a ½ inch tall, ½ inch in diameter. So it's pretty small part overall. It can be difficult to get cooling in there. And those cores were originally made out of a tool steel. So we went ahead and simulated the cooling line, the whole injection molding process using Moldflow. And then what we got out of this is we got a mold temperature result. And what we can see is, again, what we're looking for here is to achieve a uniform mold surface temperature. So ideally, we'd be seeing one single color for our part. But what we can see is that in these deep cores, we're seeing a lot of temperature gradient. And roughly, if we look at where the blue is to the red, we can see we have almost 80 degrees Fahrenheit temperature gradient from the tips of those core inserts to the base of the inserts. And so when we look at how that influenced our part performance, we were running those tips so hot that the material wasn't even setting up and the material was bubbling at the surface, and we saw a lot of poor surface aesthetics on our molded part, and even some porosity in our part. You can see that we don't even develop a full wall where we need the structural integrity for our part. And so this is going to weaken the part by not having that ideal cooling. And again, we can see on this mold on the actual part, we can see that we have a rough surface here at those base of those cores. So then we went ahead and we did some simulation iterations before investing in more molding trials or modifying the tool. We went ahead with simulation, and we did one simulation that said, okay, how much longer would we need to make our cycle time in order to maintain cooler steel temperatures, and how much and how much benefit would we get if we keep the cycle time similar, but change those core pins to a high conductivity mold max material instead and run that same process. And here we can see side by side very quickly, very clearly how our mold temperature distribution in these cores would change. Case one, this is where we started, where we had the heat temperature distribution issue. In order to cool those tips of those cores, we would have to double our cycle time. So basically, we're doubling the cost for us to manufacture this part from a production standpoint. And we can see we only get down to 231 degrees Fahrenheit. However, we can go ahead and change these cores into that high conductivity insert, that mold max material, and we can only increase our cycle time a small amount, and we can get an overall much more uniform mold surface temperature, where that's going to yield a higher quality part and drive down our cost. So in the end, the customer elected to go this route, and they were able to produce good parts at pretty close to the quoted cycle time. You know, another application here, when we were talking about how cooling influences dimensional stability of our part. Here we had a medical housing where we were seeing after the part was ejected out of the mold, the sidewalls on this part were collapsing in and was preventing assembly to a mating component. Here again, we are dealing with an acetal material. So we went ahead and we modeled in the cooling line layout for the part and simulated the injection molding cycle with Autodesk Moldflow. On the cavity side, where we don't have a lot of heat load, you can see we just have drilled lines, these blue lines right here. On the cavity side, on the core side, because of the size of the part, we had very similar cooling lines. But you can see we have much more depth, much more detail in our mold housing on the core side than the cavity side. So when we run the simulation, we can look and we can see that we have high temperature, relatively cool temperatures on the cavity side, but much higher, much more cooling variation for our part on the core side. So much less uniform cooling on this part, which is going to lead to our part warpage. And so when we saw this, we got our part warpage at about 13 thousandths in on each sidewall. That matched very well with reality. So what we had to do is we had to work with the tool maker, and we had to figure out how could we cool this part more uniformly without taking up interfering with the ejection system or any of the mold actions. And so here what we did is we went ahead and evaluated changing the inserts on the core side to mold max material and integrating bubblers into our parts. So we can model not only cooling lines, but bubblers and baffles in our system too. And you can see here with a bubbler, we're minimizing our footprint so we can design around our ejection system and the rest of our mold assembly components. And by doing that, we were able to reduce our part warpage by 50%, which allowed the parts to be assembled in manufacturing. Again, by proactively finding that simulation or finding that solution with simulation, and before we jump into modifying our tool, we're able to validate our direction and find solutions much quicker. So after we have the mold design and we have the steel selections and we have our part design optimized, usually then it comes down to getting the part in the press, and we got to optimize the heating efficiency and the cooling efficiency of this mold. This is usually left to the production floor. And so here we're talking about what cooling media are we going to use for our part, what coolant inlet temperatures are we going to set for this mold, and what type of flow rates are we going to achieve for this mold as well. If we wait all the way till we have a mold design without proactively designing it, we'll be very limited in what we can choose for these options. And usually it's the heat extraction from the mold into the coolant that is one of the driving and restrictions for optimizing the heat extraction out of the mold. The thermal conductivity of the steel is very high, so we're going to see a very steep gradient here, temperature gradient through the steel. The plastic, once it gives off the heat, it's going to be able to be extracted very fast. However, we need that coolant, this water or oil or steam, to be able to extract that heat, take that heat away from that surface so that we can maintain this large temperature difference. And so that's going to be looking at what coolant media we use and how fast and at what temperature we're going to push that through the mold. So the mold temperature is influenced and stabilized by the cooling media. We're often using water, steam, glycol, oil, all of which we can simulate in Moldflow. We can also simulate electrical cartridge heaters if you're using molding high temperature materials such as PEEK or polyimide materials. You know, when we look at our coolant medias, we have water and we have oil. And so what we'd like to be able to do is we like to use water as a material. It has a nice low viscosity that allows us to achieve turbulent flow in our materials. If we pressurize the material, we can get up to 300 degrees Fahrenheit water temperatures to heat our molds. It's also a very clean coolant media, and it's abundant. You know, everybody has access to water here for the most part, so it's very easily done. However, sometimes with high temperature materials, we do use oil where we're trying to achieve mold temperatures above 200 degrees Fahrenheit, and we don't have access to that pressurized water. But this is a high viscosity, much higher to achieve turbulent flow. It has a lower heat capacitance, meaning it's going to heat up more easily, not be able to extract as much heat per unit, and it requires a special unit. Also, any of us that's dealt with oil knows that it's dirty and it can be difficult to clean our parts. So for medical, it can be a very difficult media to use. You know, we mentioned turbulence. You know, we want to make sure that whatever cooling media we're putting in there, we're achieving turbulent flow so we get better heat extraction out of our mold. Here we're looking at a graph showing how the Reynolds number or how the characteristic number for turbulent flow influences our heat extraction. When we're in what's a laminar phase, you can see our heat extraction is very low. But as we get into turbulent phase, we see an exponential growth in our heat extraction ability because we introduce convective heat transfer. When we're talking about turbulence here, we're talking about creating unstable flows. So we're constantly bringing new material, cold material to the mold surface wall, and we're not relying just on conduction of our cooling media in order to cool this part. So turbulent flow increases our heat transfer for our part by introducing convection in addition to conduction. So that means that when we have laminar flow in our parts, we're going to see higher increase in our coolant temperatures in our part. When we have turbulent, we're going to see a much more uniform coolant temperature from the inlet to outlet, which is going to lead to a more uniform mold surface temperature. Here we're looking at a paint can design. If we keep everything the same from the cooling line perspective, but just change our coolant flow rate from one state to another, we can see that with everything else held constant, we can address some of those hot spots by just pumping more coolant into the mold because of that turbulent flow phenomenon. You know, we're using temperature control units, so the one thing we do need to consider when we're considering what coolant to use is how much pressure our temperature control unit can achieve in order to achieve these flows, but that can easily be done with simulation. You know, the other thing to look at in terms of water versus oil, you know, and turbulent versus laminar, one reason we like water and more people are going to these high temperature coolant temperature control units is because water has a much higher specific heat than oil. It's got a higher thermal conductivity as well, and the viscosity is much lower than oil. And so we're able to have a higher thermal diffusivity with water than we are with oil. So to highlight that as a case study, here we had a medical canister housing where we were molding out of a high temperature polysulfone material. And so we went ahead and we modeled in the cooling lines in Moldflow, and we modeled in the drilled lines, these blue lines, and the yellow baffles. The yellow lines represent the baffles in our circuit, both on the cavity side and on the core side. And you can see on the cavity side, we have lots of cooling integrated into our mold. On the core side, we have limited space, so we have less cooling in the core side of the mold overall. And so we did two simulations where we changed the coolant media from oil to pressurized water, and we kept the cavity coolant inlet and the core coolant inlets at roughly the same temperatures, but we were able to cycle the mold much faster with the pressurized water than with the oil. Now, how were we able to do that? Well, because the water, we were able to achieve turbulent flow, we get that better heat extraction, we're able to address the hot spots in the mold better with the water at a faster cycle time than with the oil. When we weren't able to achieve turbulent flow with the oil, we get very high mold temperatures where our baffles end in our mold. With the water, where we're able to achieve turbulent flow, we can have much cooler mold surface temperatures, and we can reduce the cycle time for our part, which in the end is going to improve the quality of our part by cooling more uniformly and reduce the cost by allowing us to cycle it faster. And again, we can quantify the improvement in our cycle time with injection molding simulation by looking at what's called the time to reach ejection temperature, and we can see that not only are we saving 20 seconds of cooling time for allowing the material to reach the ejection temperature, so we're sure the part's going to be fully set up before we try and pop it off the tool. But again, from that previous analysis, the mold surface temperature is also going to be cooler, and it's going to be more stable for a production cycle. So hopefully throughout this whole presentation, you have seen how complex and how we have all these interrelated aspects of the mold cooling when we're trying to design these molds that need to be considered holistically. Using simulation can help us optimize the cooling conditions to weigh the cost benefit prior to having first shots or prior to having a full mold design implemented. And so we can improve how our part's going to perform. We're going to reduce the cost to our customers, reduce the cost to us, while improving the quality for our part overall. So with that, I'd like to, we're recording this today, but I'd like to open it up for questions. You can do that either two ways, by reaching out via email to myself at the email shown, or to my counterpart, Brandon Kingston, at D3 Technologies, with anything on how, if you'd like to see a demonstration or understand what other results you can get out of the cooling line analysis and cooling analysis from a part like Moldflow, a simulation package like Moldflow, we'd be happy to do that. Also, if you'd like to hear about something else, we'd love to hear about what else you'd like to see our webinars be about. Our next webinar after this one is going to be on June 3rd, and there we're going to be talking about bringing everything together and how we can use Moldflow to reduce our part warpage and get parts right the first time using injection molding simulation. And with that, I'll hand it over to Scott, and you can feel free to reach out to D3 with any further questions as well, or the Madison Group.
Yeah, perfect, Eric. Thank you very much. Yeah, so that really concludes the webinar today. If I have any questions or would like to see any additional information, feel free to reach out to Eric, Brandon, or myself, and we'll get back in touch right away. Thank you, everyone.